Hello. It's good to see you back again. Wednesday evening revision. Let's get to it. We're just going to carry on with the paper one that we were doing in the last session, which was last Thursday. I'm just checking to see that my feed is working. Hello. Yeah, and it is good. Okay. Hello. Right. So let's get started, and I'll just might as well just get on with it. And I've got everything here. There we go. And so, hope you're ready to do some questions. We are going to continue on. If you remember, we were looking previously at, we did a bit of von Neumann architecture, and we answered this question here in the paper. It's the March 2024 paper, and we answered that question there, and then we need to look at, we did this one here, did all about von Neumann and cores and processes and cache, and now we were up to this one here, which is question C. The computer has both primary and secondary storage. Random access memory is one example of primary storage. Describe what is meant by RAM for 2 marks. Remember that they've said what RAM stands for, so don't put that in because you won't. Well, I mean, if you put it in, you won't get a mark. So, how would you describe RAM? So really, when they ask you questions about RAM, what they're really looking for is kind of 2 things. One, that it's volatile memory. So volatile means that if you switch off the electricity to that memory, it loses everything. So that's volatile. And also that it's storing all the sort of data and instructions or programs that are currently running. So that's kind of what they're after. Someone said recently frequently used instructions. Not quite. It's whatever's currently running. So rather than what's frequently used, it's what's running. So if we have a look at the mark scheme, what have they got here? Yeah, they've got it here. It's volatile storage, stores data for the processor to access directly or quickly. Directly accessed by the CPU. So I don't know, they might give you a mark for that second bullet point, actually. They might give you a mark for that one, actually. And yes, stores currently running data and instructions. Okay, that's our RAM. Then we've got a question about ROM. Read-only memory is another example of primary storage. ROM often stores the startup instructions for the computer. Identify one other item of data that is commonly stored in ROM. Yeah, BIOS is another one, good. Or you could say firmware, or you can say bootstrap loader. What else have they got? They've got BIOS, or you can call it the bootstrap loader, firmware, or part of the operating system. So yeah, not long. Not long for your mock. All right, so let's have a look at the next question. Some computers make use of virtual memory. State the purpose of virtual memory. Why do we have virtual memory? So basically, virtual memory is there. We use it because we've run out of normal memory or RAM. So we create virtual memory to basically act as RAM. It's not actual RAM, but it acts as RAM. So to run programs when there's insufficient RAM to run them, to allow RAM to store more data when required. They do seem to like to ask questions about virtual memory. It's one of their favourite subjects, although normally there's more marks. Normally they ask a bit more detail, but anyway, let's move on. Now we've got a table here. This is one of their favourite styles of questions, where we've got a table with either a meaning or a description, a function name or a description, and you've got to fill in. So we've got managing memory. So it's complete the table by writing each missing operating system function, name and description. So what is managing memory in an operating system? And then we've got a description, allows application software to run on the computer. What is the function of an operating system that lets you do that? And then the last one is you've got to describe how an operating system manages peripherals. And you don't need to write much. It's literally, I know they've left quite a big gap for description, but really you only need to put like one short sentence for each. So it's a bit strange how they've given you a lot of space there. I think for this one, it's quite hard not to give a circular definition. So what is managing memory? Well, it manages the memory. So yeah, let's have a look at the answers for this one. So they've put examples. So if you put something that isn't here that is correct, you will get a mark. So managing memory, it allocates memory to processes, prevents two processes accessing the same memory. What allows application software to run on the computer, it's the fact that it's, for an operating system, it's a platform for running applications. And then how can you describe managing peripherals? Well, it allocates data to buffers, transmits data to hardware. So for peripherals like, for example, a printer or a scanner. So it transmits data to the printer, receives data from the printer or the scanner. That's what it's on about there. Yeah, so a bit of a weird one, that one. But they do like this style of question very much now. There's usually one in each one. So the operating system handles interrupts. State the purpose of an interrupt. And then identify one input device and one example of an interrupt that it can generate. You're all very quiet today. Okay, so let's have a look at that. So what is an interrupt? An interrupt is something that basically says to the CPU, I need your attention, stop what you're doing and process this thing now. So they've got to indicate that something requires the attention of the processor, operating system or the CPU. And then identify one interrupt device and one example that it can generate. So they've got a keyboard, because every time you do press a key on the keyboard, that is actually a hardware interrupt. Just trying to memorise it's fine. Or a mouse. So a mouse could be where you move the button clicked. That is also an interrupt. You could also say, for example, out of paper on a printer, scanner, I don't know, can't work, or button is pressed down when it shouldn't be. Literally, it does say, e.g., and if it says that, any valid answer that you come up with that is some kind of input device. Well, they've said input device. So actually, my example of a printer wouldn't be a good one. So yeah, input device, keyboard or a mouse is pretty much all that you can do, really. I suppose you could have like a game controller. That would work. Yeah, so an interrupt is something that it's like an alert to the CPU, usually the CPU, to say, stop what you're doing, I need you to do something. Like, and the examples here, pressing a key on the keyboard, clicking your mouse, moving your mouse, they're all interrupts. Now, the next question does go into interrupts more. So let's have a look at that. It says, and there's 5 marks for this, a processor is currently executing a program. The processor receives an interrupt. Explain how the processor manages the current program and the interrupt. And there's 5 marks for this. So don't worry if you can't remember any of this. I will go through it in a moment. But do try and just have a few minutes to try and think what might happen when the processor gets that interrupt. And do think about the example that they've got in the mark scheme here. If someone presses a key on a keyboard, what happens to the processor? Okay, so I'm going to go through this now. And actually, I've got whiteboard here because I think this is a good chance to kind of go through interrupts and interrupt service routines. Is it double R? It's probably not very important. It is double R, interrupts. Okay, so what happens when we get an interrupt? Let me just summarise what type of interrupts you can get. So you can get, like we saw previously, a hardware interrupt, like keyboards being pressed or a printer saying out of paper. You can have a software interrupt where it's some kind of error in your code and it kicks up a big error and your CPU has to do something. And there can also be user interrupts as well. So for example, the user types in Control-Alt-Delete and on a Windows machine, and that sort of kicks a whole different menu up for you. So there are the different types of interrupts. So what happens is we've got an interrupt coming in. So it's one of these interrupts. We'll pick an example just for this. So I will say it is a let's use the example that they had, the hardware. So we have the user presses a key on the keyboard. So they press the letter H, for example, on the keyboard. So what happens is that interrupt is sent to the CPU. The CPU gets that interrupt and it says, okay, what is the priority of this? What is the priority? So actually, I'm going to write this over here as well. So I'm going to say the CPU receives an interrupt. So I'm going to give you the proper answer. The CPU receives the interrupt. And it is worth persevering with this one and staying for this one because they do like asking questions about it. So the CPU receives the interrupt and gives it a priority. And you don't have to worry too much, but you know, i.e. low, medium, high. Now, if it's low, then it'll probably just ignore it. If it's medium or high, it might think, actually, I need to do something about this. And normally, if you're pressing a key on a keyboard, that is fairly high priority. Now, anyway, it's given a priority and there is an interrupt queue. Now, interrupts are really important to make sure that computers aren't just sat there waiting around for things to happen. Because if you start, you know, if your computer's doing something in the background and you press a key and it thinks, oh, it's low priority, then nothing's going to happen on your computer because, you know, you could be streaming something like, I don't know, watching whatever you are watching on Netflix and you press a key because you want to, I don't know, you're writing an email at the same time or something, I don't know, could be anything. Well, you'd have to wait like possibly minutes, even hours, or until you sort of click the mouse to say, I don't want to watch this thing on Netflix anymore before anything happened. And there's lots of internal interrupts that happen as well. So although those three examples are the main ones, there are other interrupts that happen. Anyway, we have an interrupt queue and the interrupts are listed on here and it's put on the queue. So our interrupt is added to the queue. And each of these interrupts might get run. So obviously it's like a list and it will run through them in order and pick out which one, you know, it should do them in order actually. Normally it will do them in order. So what happens next is, once it's on the queue, so I'll put the CPU receives the interrupt, gives it priority, low, medium, high. It's then placed on the interrupt queue. Then what happens is, when the CPU has finished its current fetch execute cycle, which it can do millions, possibly billions of, so you can see that these interrupts do get serviced quite quickly. So when the next fetch execute cycle finishes, the CPU checks the interrupt queue and may run the interrupt. So like I said, you know, realistically, they get dealt with very quickly because it's doing millions of cycles per second. So it may run the interrupt, it might run the high, so that might be a high priority. We've got a high priority here, that one's low, that one's medium, that one's high. So it'll run the high ones first. So checks interrupt queue may run the interrupt if it's high priority. And then assuming that it does, so when it runs the interrupt, or when it runs an interrupt, it stops what it's doing. And it kind of parks everything. So it stores current registry values. We've already got our 5 marks, by the way. In a temporary place, runs the interrupt, and then goes back to what it was doing again. Or what it was doing previously. So you can kind of think a bit like, you know, if your parent is in the garden, for example, doing some gardening, it's a lovely summer's day, and you go out and you interrupt them. They're currently doing something, so that your parents are the CPU, doing some gardening in the garden, and you interrupt them, and it's like, hey, mum, dad, or whoever it is, there's a fire in the house. Well, that's high priority, isn't it? They're going to go and help you straight away. But if you go and you say, hey, mum, dad, that my favourite TV program's just come on the TV. They're like, well, that's low priority. They're not really going to want to do anything with that, if you see what I mean. So fire versus TV programme, high, low priority. Which one are they going to go? Well, they're going to go for the high priority. So that is basically what the interrupt does. How I would answer it. So so let's have a look at the mark scheme. There is a few extra bits in the mark scheme. I don't know whether you need to put this much detail in it. But for your 5 marks, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 possible things that they've got on it. Maximum 5. The interrupt priority is given and placed in the interrupt queue. The processor finishes the current fetch execute cycle. The processor checks the interrupt priority queue, or checks for higher priority interrupts. If lower priority processor runs, next fetch execute cycle is run. So basically, this bit here, this bullet point here, it's not very well worded, but it's saying if the lower priority processor continues with program. So what this one here is saying is if there's low priority interrupts, it might not run them and just carry on with what it's doing until it's finished what it's doing. But if it's a high priority one, then it will stop what it's doing. It will check the source of the interrupt, cause the appropriate interrupt service routine. So this is, I didn't put this in my answer, but interrupt service routine is just basically a way of handling, it's part of the operating system that handles the interrupt. And it does the interrupt. And if there's other high priority ones, then it might do those too. And then it goes back to what it was doing previously, basically. And it's because it's put all its registry contents into the into sort of temporary space. Is it better? Someone's asked, is it better to write fetch execute cycle or fetch decode execute cycle? Yeah, it doesn't matter which one of those. They'll know which it is, and you can use it interchangeably. Yeah. I'll just put my answer back up there again if anyone needs to screenshot it. But that should get me, there it is. So get the interrupt priority, placed on the interrupt queue, CPU checks the queue. If it's high priority, it runs. Yeah, there's about 6 or 7 marks there. I mean, that sort of thing used to be in the A level. It still is in the A-level, actually. So a lot of this is, this particular question there, it's A-level. Let's look at the next question. Let's move on. That's the mark scheme. So the next question, you've got to draw and annotate. So label means label. Draw and annotate a diagram to show the process of a user entering a URL into the web browser, displaying the web page. So user enters URL in the web browser. Draw and annotate a diagram to show the process from the user entering the URL to the web browser displaying the web page. This is a really important process to learn, actually. They ask a lot of questions about this one. This is a very typical paper. And also, I'm just going to go into URLs as well, because it's very important that you know what a URL is made up of. We'll do that afterwards, though. Okay, so try and draw your diagram. Make sure you annotate it. Most of the time with these ones, if you have to draw something, all you do is draw boxes and write, with arrows as well. So while you're doing that, someone's asked in the chat, is there a lot of difference between Cambridge CAIE and OCR computer science? Because there's a really good revision platform you use, but it only has OCR. So yes, they're very similar, but no, they can be very different. So about 80 to 85% of the content is the same between both GCSEs and the IGCSE. And in actual fact, Cambridge CIE is owned by OCR. They're the same sort of umbrella company, but the CIE one does the IGCSE, the international GCSEs. Anyway, to get to your question, the really big differences you'll find is in the exams, the style of the question. So if you look at the OCR exam paper questions, they are very different to the Cambridge ones. And you'll also find that the pseudocode is very different as well. And the paper 2 style questions are very different. There's also a few differences in the syllabus. So they have more sorting algorithms in OCR, and they also have So we have bubble sort in the Cambridge one, but they've got bubble sort and merge sort, I think it is. And then searching as well, they've got binary search, but Cambridge doesn't have binary search. So it's, yeah, the big difference though is the pseudocode. It is very different, and just trying to think what else. I think also, yeah, in OCR they only have 3 logic gates, whereas in Cambridge there's 6. I think most of the database stuff is about the same though. Yeah. And most of the content is sort of with the Python that you need to learn, that's the same. So yeah. So I mean, it wouldn't hurt you to try, you shouldn't run out of past papers. If you run out of past papers for this, then I would probably say do the pre-2023 papers rather than OCR. Because you might be looking at questions and think, hang on a minute, I didn't cover that in my lesson. And it's like, well, because it's not actually in there. Oh yeah, in OCR they cover network topology, and that's not in Cambridge. So you can see that there is a few differences. And if you didn't know, then you might think, oh no, I've got to learn that, and it's going to come up, and you're revising it, but it isn't actually going to come up for you. Someone uses save my exams and the notes from the lesson. Yeah. Now, talking of revision resources, this question here is actually in the revision cards that you've got in the revision pack. And if you're not one of my students and you haven't got the revision pack, you can purchase it for the bargain price of £9.99. All my own students who are either live or pre-recorded students, you get those for free. But anyway, yeah, it's like multiple choice. Yeah, they should be okay. They should be okay. I mean, if you want to use the OCR, I mean, I've got a couple of OCR videos on the channel. If you want to have a look, I think the Cambridge one is slightly harder, actually. I think, yeah, but especially like there's particularly one question where you've got to just draw boxes around for flowchart, whereas in Cambridge they make you write the whole flowchart. Let's have a look at this uniform. We're going to annotate a diagram for entering a URL. So, like I said, there's a diagram for this in the notes, in the revision cards. Let me just open it up. Okay. So the first thing that happens is we've got our computer, or your computer, and you type in the URL, and that goes to your internet service provider. So the URL goes across here. This is number 1, and it goes to your internet service provider, and they have something called a DNS, domain name service. And all that is, it's a fancy name to say you've typed in bbc.co.uk, and the IP address of that is 194.215.2.4. And they've got other things in it, like, I don't know, Amazon, and that is 212.214.2.4, etc. And it should have most websites in existence. And if it doesn't, it can find that out. So it looks up what you typed in. So say, for example, I typed in bbc.co.uk. It will then return the IP address. So it returns the IP address of your URL. Remember, the IP address is the internet address. Then the next thing that happens is we use that IP address to request the web page from the server. So say, for example, yeah, so there's the web server. Actually, I'll do the universal sign for a web server like this. So there's the web server, which is at 194.215.2.4. And then the web server says, okay, here's my web page. Here's my HTML web page or web pages. And then the last thing, so that's 1, 2, 3, 4. And then the last thing is your browser displays the HTML. Now, obviously, this happens very quickly, doesn't it? When you, again, because computers are fast, who knew? This will happen really quickly. So this is what they're after. And like I said, this is in the revision cards. There's a card for it. And it is important that you learn this because they will ask questions about it. It's one of their favourite questions again. Now, just to go back to URLs, let's just have a look at URLs. Remember that we've got a protocol. So that's our protocol here. And obviously, if it's a web page, then it's going to be HTTP or HTTPS. And then we've got the website. So it could be www.bbc.co.uk. And then / iPlayer, for example. So this bit here, this is the domain name. And then the last bit is the path, or you can say the file as well. So it's the path or the file. Either of those, you should get you a mark for that. Now, that isn't in the question, but I'm really surprised at how many people don't know this. And they love asking this question, again, in the exam. And I always look at it and think, oh, it's so easy. Why are they asking that? And so many people get it wrong. It's like, you don't know that. It's really important. Yeah, it's not a sponsored video. Okay, so if we just have a quick look at the mark scheme for that, you can see, I mean, they've got so they've got, a few other different bits in it, but essentially it's the same as mine. URL from the computer to the DNS. DNS looks up for the IP address, sends it back to the computer. The browser then requests the web pages from that IP address, and the web server processes it and then sends it back to your computer, which then displays it. Now, obviously, this isn't taking into account any asymmetric encryption. So what I mean by that is the HTTPS bit. The S is secure, and that means it's encrypted. So we haven't included any encryption in this, but that I know that comes up in other exam papers, so hopefully we'll cover that. But that's also in the exam revision card, so make sure you've got those. How long have we got left? Oh, we've got just enough time to do another question. Let's do the next one. Oh, it's filling in the gaps. Complete the description of digital currencies. They don't seem to ask this quite so much now, but you never know. Complete the description of digital currencies using the terms provided. Blockchains, change, etc. So we've got digital currency does not exist something. It can only be accessed electronically. Some digital currencies have digital ledgers called something else. These are decentralized databases, so where transaction is stored as a new set of data with a something and is linked to the previous set of data. This means that transactions cannot be altered, only new transactions added, which allows the location of the data to be something. you can see the sort of style of questions actually, filling in the gaps. This is another one of the style of questions that is often in every single paper, every single sitting. There's always one of these types of questions. I quite like them actually. Okay, so yeah, so Samaya has put in the chat the correct answers. So it says a digital currency does not exist physically. It can only be accessed electronically. In fact, let's look at the mark scheme. There we go. So a digital currency does not exist physically. It can only be accessed electronically. Some digital currencies have digital ledgers called blockchains. These are decentralized databases where each transaction is stored as a new set of data with a timestamp and is linked to the previous set of data. This means that transactions cannot be altered, only new transactions added, which allows the location of the data to be traced. Interestingly, like I know everyone's talking about AI, so this is just a slight aside thing here, and everyone's talking about vibe coding and AI and all this type of stuff. And, you know, 3 or 4 years ago, it was all about blockchains. They're gonna take over everything, and that sort of died death. I mean, I know there's still Bitcoin, which has plummeted in value over the last week or so, and there's other digital currencies that are available, but yeah, it's they have a purpose, but they didn't quite sort of take over like everybody said they would. There was some people selling, like, you know, blank paintings for tens of thousands of pounds, and everyone's like, who would buy a blank painting for £10,000 on a blockchain? And it was because it was all just money laundering. So really, that's the legacy of blockchain, is that just loads of people are using it to launder money. Anyway, so that is that question. We've run out of time, so we'll continue tomorrow and carry on. We've got the next question. Have we got a few questions here? A bit about AI, self-driving tractors, farmers. Oh, there's quite a few questions still, actually. So yeah. Anyway, we'll continue tomorrow. See you at 6 o'clock tomorrow night, or maybe tomorrow at 10 o'clock for Improve Your Python. Take care, everybody.